No pressure.
Right. Okay. Hi. Okay, I don't want to oversell this too much, but yeah, so my name is Mikola. I'm a graduate student in Wisconsin. I have a blog, 0FPS, and I've written about a bunch of, kind of oddball hobby projects like voxels and Minecraft and time travel for video games and other things. But today I am going to talk about multidimensional arrays and scientific computing. So, oops. Why should you care about this? The sort of simple explanation is that multidimensional arrays are really useful, and there are a ton of different problems or domains where you can throw these things at something and make your life easier or make something faster or do something really cool. And so I could explain this, by just like enumerating a bunch of different problems. But I figure what I'll do right now just to get things started is just show a bunch of demos, and then I'll kind of go through after the fact and explain why this works. So, one of the basic operations is you might want to do like image processing, for example, like filtering, like take an image or blur it, or you could do edge detection or other types of transformations. So this is, like basic image processing stuff. You could also want to do something like visualize. Oh shoot, this didn't work. Okay. You might want to do some sort of like digital signal processing thing. So you could actually like take a sound and play it back at a different rate. So, oh man, this is like bad. Like the sound's not working here. Okay. It's plugged in. Oops. Okay, there we go. Right. Okay, all right. Let's start this over. So here, this is basically
77 years ago,
our fathers brought forth on this
continent a new nation,
conceived in liberty,
and dedicated
to the proposition that all men are created equal.
Yeah, so what this is doing is this is basically like in real time, basically doing dynamic time stretching for a sound, so you can do like pitch shifting stuff. So this illustrates that you can use, multi-dimensional arrays. In this case, it's kind of like a pair of one-dimensional arrays to do, signal processing or audio stuff. And it's also useful for, of course, scientific computing. Like, this is like a Gray-Scott model. So this is a type of partial differential equation, and this is just being updated in JavaScript in real time. And there's, of course, like lots of other interesting little demos that you can do with this. So these are all different things built on that. So, NDARRAYs are used in voxel.js, of course. There's a variety of other different demos here. So I'm going to open this in a new tab. Yeah, okay. And so here's like a little, voxel sphere. We can load up other stuff. So, what's going on is this is like taking a model of a teapot, voxelizing it into an array, and then rendering it as like a little voxel mesh, or you can do it with like, Stanford Bunny, and you can also show like the wireframe. So all of these things are built on top of NDARRAYs and, implemented using this, collection of modules that I've put together. So these are just like different, sort of Minecraft-esque voxel things. So I'll close this tab and get back to the presentation. So, right. So multi-dimensional arrays are cool because you can do a lot of cool things with them. And there's a couple of different ways you could consider implementing multi-dimensional arrays in JavaScript. And so if you're just starting out, probably the easiest thing to think of is to just create an array of arrays. So you would just maybe create a 2D array by allocating a 1D array and then filling that with an array of other 1D arrays. This has some problems though. So the first one is that if you want to access an element in the array, each of these arrays themselves is really an object. And so whenever you want to like look up some particular point, you have to do a sequence of D object dereferences, where D is the dimension of your array. So this would like maybe like increase in 2D the amount of work you have to do by a factor of 2, or in 3D a factor of 3. And so that's pretty slow. The other problem is that storing all these extra object references requires an overhead. So you actually have to store n to the d minus 1 extra like arrays, where I'm using n here to represent like, sort of the linear dimension, and then d is the actual, dimension of the array. And if you want to do something like walk over the array in order, each, successive operation requires, another dereference from this giant blob of arrays. So there's this huge overhead, and nothing is going to be arranged coherently in cache. And then if you want to do things like slice it, it becomes really slow. Although I should actually put an asterisk here, because as I learned from Mr. Aleph, you can actually optimize this in a very kind of set of special edge cases, but it's extremely fragile. So there's like a way you can kind of make that a little better, but there's still reasons you might want to go beyond it, because maybe you want it to work for sure. So, one step above this, and this is, the thing everyone goes for immediately after you try the first thing and you realize it's too slow or it doesn't work, is you just pack all of your arrays into one array, and then you do the indexing manually. So this means now that, okay, you have to do like some arithmetic whenever you want to look something up, but arithmetic's cheap, and it's the memory accesses that are expensive. So it becomes a lot more efficient to store your data in this packed format. And it also speeds up things like walking over the array. So if you want to, visit every element in the array, it'll now scale with the size of your cache, which is like B, the block size. So if your, computer can pull in like 100 elements at once or 1,000 elements, then this will now be 1,000 times faster than, an algorithm that just visits a bunch of completely incoherently located objects in memory. But the downside, though, is that if you want to cut out like a subarray or, copy a view of this and return that around, there isn't a good sort of, method for cutting out slices of arrays. So that's really the problem with this type of an approach. And, it also sort of assumes that your arrays are maybe like laid out, in like row major or column major order, and perhaps, you maybe get data that's in the wrong format, and then you have to do an expensive transpose operation. So the last sort of, approach to do this is you could also try to use a strided array. And this approach is what's used by most scientific computing libraries and packages. So for example, SciPy and NumPy will do this, and or under the hood, they hide a lot of the details from you. All right, but this is how it's usually implemented. And so the idea is that instead of using a fixed stride, where you would basically fix the size of the array in memory, you make that a variable. And so you just store the stride as like a little vector along with the shape, and you also store an offset into the array. And then lookups, you just multiply these parameters from the stride in order to get an index in there. So it's still really fast to do memory accessing, as before, right? Because it's just multiplied by a stride instead of multiplying by a shape. So that's pretty much the same as before. We have to store an extra, D words of memory, but that's nothing, so it doesn't really matter. And we can still do fast traversals. But the big thing, though, is that now if we want to do a slice operation, it's just a matter of creating a new stride and offset. So that will, speed up like cutting out views of arrays, so we can, very easily take chunks out of an array. So I'll explain that now in a moment. So this now brings us to NDARRAYs, which are an implementation of this basic idea in JavaScript. And so, like the bigger ambition, like the grander concept, is to eventually create a basic platform for doing numerical and scientific computing in JavaScript. And where this approach differs from other projects like SciPy or NumPy, which tried to bundle everything under one gigantic central authority that controls whatever features get added or removed, and then there's like a little tight governing board that runs it. The goal with NDARRAYs is to create a very minimal core language that you can use to pass or communicate multidimensional arrays between different modules. And then the functionality can just be extended by whoever, whenever, however you want through the tools that NPM and Browserify have given us for publishing and authoring code. So the basic idea is that we're going to use strided arrays, but we're not going to put it all into one giant like central core. We're going to distribute it out, and everyone can create their own modules or their own functions. And so eventually the idea is that this should become some ecosystem of different modules that can communicate with NDARRAYs that should be able to match like SciPy or NumPy in functionality, but you'll be able to write all of this in a browser, and so you won't have to redistribute like a 2 gigabyte pip install of NumPy that probably isn't going to work the same on my system as your system and has a bunch of like native Fortran dependencies. You got to install 20 years of compilers in order to get to work. So this is going to be like long-term, something that maybe can actually let you do credible scientific computing in a browser. And to make this fast, we're going to do a sort of explicit memory management. And there's also a very important view towards keeping everything as sort of close to what you can represent in WebGL as possible. So you can use these data structures for things like packing stuff into WebGL buffers and pushing it out to the GPU. So yeah, so here's the basic rundown of how the core NDArray library works. And there's not a lot in there. So the way you do this is, using common.js require, you just load the NDArray thing. This is what you get from module.exports. And then you can construct an NDArray by passing it a set of parameters. So you give it a data, a shape, a stride, and an offset. So the data is basically the underlying 1D array data store, and this can be a typed array or a buffer or whatever you want. And it just has to be addressable, as like a linear blob of memory. The shape is basically like the n-dimensional shape. So if you make a 2D array, you would, pass it like a little length 2 array of different parameters. And then the stride is, how you calculate the actual coordinate in the map. So these are, the coefficients for the view of the array. And then finally, you have an offset. And you can, of course, skip these things, and they will default to sensible values. So for example, if you just pass in the data, it will create a 1D ND array. If you give it the data and shape, it'll assume a row major layout, just like C, and it will create, the correct like stride and offset. Or if you give it a stride but don't specify the offset, the default is 0. So you can basically pass it just as much as you need from these things, and it'll fill in the rest reasonably. So that's the basic constructor, and once you have an ND array, you can then do stuff like update an element, where you basically call array.set, and you give it a pair of indices for the 2 coordinates, and then a value that you want to set it to. So this would basically translate into, using our previous notation in variables, as we just take the data array and then we multiply it with our stride vector and add our offset and set that equal to v, right, which is this here. So that's the basic idea. And there are other accessors too. So that you have basically the same story for get, and then there's also a .index, which just calculates this quantity here, which is useful for various other operations. But the interesting thing that you can do with this is you can do slices. And each of these operations is done in constant time. So in Python, there's like a lot of operator overloading and fancy syntax associated with this. But in JavaScript, which is basically how this all works, it doesn't use like any kind of fancy pre-compiler or whatever. You don't have these kind of like cute little notations for using ... or colon or whatever for specifying a range. So I kind of invented this syntax here, which I think is a very simple and easy way to specify different slices. So the first one is there's a method called .high, which just reshapes the array. There's a method .low, which moves the offset of the array by basically shifting the upper left corner of the image around. There's transpose, which will basically like transpose the array in place. You can also do step, which changes like how fast a stride moves. And you can also select a subarray using .pick. So if you take like, you pick the first component or whatever, then it'll fix that guy to a specific value, and then you get a lower dimensional subarray. And you can chain these things and compose them, and each of these things is basically ordered dimension because it just creates a new ND array view, and it doesn't copy the underlying data store. So in terms of memory accesses, each of these operations is constant time. It doesn't update the underlying array or anything. So that's maybe a lot to take in, but to illustrate it, I put together a little visual demo of all this. So here is basically like a little JavaScript terminal here, and as I'm typing this in, it's evaluating this expression and creating a new ND array. So if I just take the array by itself, I have a view of the image here. So this is like a little, lorem ipsum test image type thing. And it has basically the following properties. So it has a 512 by 512 by 4. So it's like a 3D array. The last one is the color components. And then here's the stride data. So this is basically how this thing is laid out in memory. And then this is the offset. So if I do something like, say, take array dot high 256, it'll take the upper left quadrant of the image. And I could then chain this by doing something like .low 100, 100, and it'll cut out this little region. Or similarly, I can cut these things out in different orders. So I could do something like .low 100, 100, and it'll cut out this sub-region of the image. And then I can follow this up by saying like dot high 256, 256, and it'll cut out like an array of size 256 by 256 starting at offset 100, 100. But this is just like the simplest stuff you can do. You can also transpose the image. So I can flip it by passing it a permutation, and it just reflects the array in place. So nothing has to happen, doesn't have to update it. Or I can do something like take every other pixel, and now I've got an image that's half the size, right? And it just does that automatically. Or I could do something like reflect it in place, and now I can flip it around. So I can go pass it a negative step, and it'll just change the index, and I can flip it like that, whatever. So different ways to do the same thing. And then finally, I can also like pick out the different components. So I can do something like just select the red channel from the image, and this is what I see. Or I could pick out just the blue channel, or this is the blue channel. Last one was the green channel. But you see the idea. So this is the basic kind of notation, and each of these operations is free practically. I mean, it's the cost of creating like a tiny temporary object. So there's literally nothing going on under the hood with that. So this is the basic data structure. And the last thing is that you can also use this for sparse data too. So all you have to do to create a sparse NDArray is you can just create any object where you have a get and set and a length property, and you can pass that in as the array attribute, and then you can use that to actually implement some kind of sparse data type. So this is like how you would implement a hash-based NDArray. But there are other modules out there now that do things like run length encoding, which is actually equivalent to doing like compressed sparse row or compressed sparse column matrices. And the same math all works and all the same modules work. So it doesn't change anything in terms of the code. So, and that's because they're all just 1D stores of this data. And yeah, that's pretty much it. That's all that's in the NDArray module. And I hope I don't have to change it or like update it in the future, because I believe it's pretty much done as it is. And so I plan, and like I swear as best as I can, that I will not update that module. I will not change the interfaces unless there's a bug or something. But barring that, I'm not going to add any features to it or like try to do anything cute. It should be just finished. It's over, right? So how do we extend it? Well, we add modules. And so there's now a huge collection of modules that I've written and other people have added too that do different interesting things with NDArrays. So NDArrays by themselves, of course, don't really do a lot. They're just a notation for working with slices of multi-dimensional arrays. That's it. So if you just use like NDArrays in your project, you shouldn't expect that it'll all of a sudden be like 100 times faster or whatever. You have to actually use these modules which are built on top of NDArrays that do things in some smart way. So probably the most basic one, though, to get familiar with is NDARRAY-OPS. And so this is the same sort of idea. You just load this module and install it through common.js. And then you can basically do component-wise operations. So there's like a bunch of pre-programmed generic math functions. So this would, for example, multiply an array A in place by a scalar 2. So the general format for this library is like each thing starts with like the operation name. You give it a flag which says you either want to pass a scalar or an array as the second parameter. And then you can also say whether you want to update it in place or copy the result into another data. And then there's also some extra ones. So there's one for like just assign, which is very useful for copying an array back and forth. And there's random, which will initialize an array to different random values and all the other usual math operations and so on. So that's kind of interesting. But what if you want to create something more ambitious, like your own sort of component-wise operation? And the answer to that is you should use CWise, which is the actual guts of how all of this stuff gets implemented. So I'm going to spend just a moment on this. And here is CWise. So the basic notation is you just load the CWise module, and then you pass it some arguments and a function, and it will transform whatever code you write here into an efficient array operation. And this module is somewhat smart about how it does this. So it won't, if you have like an array that's in row major order and an array that's in another array that's in row major order, then the best thing to do is just walk over the pair of arrays in row major order to apply the operation. Or if you have one that's in column major order, you should do the traversal in column major. So the question is, what do you do if you have two arrays that are in like a different like layout in memory? And so what this does is it uses a cache oblivious divide and conquer algorithm. So it'll actually generate something that runs about as fast as the actual operation. So I had like some benchmarks with this. I don't know if I'm going to show that or not, but yeah. Right. So here's what I'm going to do. I'm going to go pull this out. So this is basically executing right here. So this is just comparing what happens if you take a column major array and a column major array. And this is comparing a column major traversal, cache aware traversal. This is basically, what? Okay, I don't know. Okay, let's try this. Yeah. This is just running the experiment right now. So this is basically like, okay, a micro benchmark. Maybe I made a mistake with it. You can see the code online if there's something wrong with it. Perhaps, I don't know. But yeah, so this is basically comparing the, sort of three major approaches. So you have column major, row major, cache oblivious, and you can see that the cache oblivious algorithm usually is competitive with the best approach for any particular layout of arrays. And the reason that you don't do the cache aware method is that generally you don't actually know what B is on a given system, and it can actually be changed by a variety of factors, like the amount of processes that are running, or how much contention you have for memory, or just whether you're running on a cell phone or whether you're running on a browser. So the cache oblivious algorithm is convenient because it will work for any B as good as you can reasonably hope for. So that's the basic idea there. Let me go pull this up. Right. So, okay, that's C-wise, and it's pretty fast. Yeah, so that's the basic stuff. There's also a collection of WebGL modules that all use NDARRAys to talk to one another. So this is sort of an ongoing project, and I'll probably have more to say about this in the near future, definitely at NodeConf in the coming months. But you can already go out there and look at it, and these all are built on top of this idea. There's also a bunch of basic utilities, so there's different memory pooling stuff, convenient things for packing arrays of arrays into typed arrays and so on, and also loading and saving 2D images and basic debugging stuff. So you can dump an image to a console.log or whatever. And then there's more, so there's also a lot of fun things, so you can do FFTs, sort an ND array in place. This actually turns out to be quite a bit faster than, for example, cross-filter or other different sorting algorithms. Binary search, there's also selection, quick select, distance transform, so there's linear time image distance transform algorithm. You can voxelize meshes, you can create bitmaps, hash tables, prefix sum for integration. There's also convolution stuff too, and other signal processing things, and you can do stuff like isosurface extraction. So here's one module I wrote recently, where you basically give it an ND array as a parameter, and it will just extract a cell complex, which is basically like a mesh, but in any dimension. So in 2D, you can use it to extract a vector from basically a raster image. Or in 3D, you can use it to polygonize a level set from an ND array. It also works in 4D and in 1D. I have an example of this. I did this last night. This is going to just look really weird, though. So here we go. So this is actually a 4D sphere loading. This is actually just rendering the SVG file. It takes a little while. But it does work in 4D. There's really no good reason to do this. You could, though, right? Okay, right, let's see. Okay, there we go, killed that page. That wasn't even done rendering the SVG file, but it does work. So, okay, that's the idea. So, all right, so how do you do all this stuff in practice? So I wanted to pick a kind of cute little example to work through and show what you could do with the ND array. So I decided to implement the Burrows-WHEELER transform, which is a pretty useful little idea. It's used in data compression and a variety of other things. So if you've ever used bzip or whatever, the Burrows-WHEELER transform is used in that. The reason that it's important is that if you basically do a Burrows-WHEELER transform plus run length encoding of an array, that actually gives you the optimal entropy encoding of that array up to a constant factor in the empirical entropy for any number of characters. So this is the mathematical significance of it. But the reality is that it's also just kind of a cool algorithm, and there's a very naive way to implement it that's kind of illustrative using multidimensional arrays. Now, this is, of course, not the fastest implementation of the Burrows-WHEELER transform as a disclaimer, but it still is kind of neat, so I'm just going to go through it. So here's the sort of walkthrough of how you do this string processing. So the first thing is you input your string, and you append a 0 to it. So this is just regular JavaScript. Then what you want to do is you want to create a matrix of all of the rotations of this string. So the way that I'm going to do this, I'm going to take my string here, banana, and I'm going to basically create an NDARRAY of 2 copies of this string with the 0, and it will have shape n by n, but instead of having a stride of n here, I'm going to make it a stride of 1. So the underlying data store is actually length 2n, and then the array itself is n by n. Right, so that's what I'm doing there. So this is actually like, you know, a 2D view of really like a 1D array of 2 strings concatenated in memory. And then step 3, I just sort it. So I basically, you know, use ndarray sort, call that on the rows of this x after cloning it, and now I have a sorted ndarray. And then the Burrows-Wheeler transform of the string is I actually just take the last column. So I take this guy right here. So that thing. And then this string here is the Burrows-Wheeler transform of banana. And I can, of course, like change this. I can add like more a's or something to the string, and it'll like update all this, you know, interactively. So that's kind of like just like a little demo thing. But yeah, so this is the Burrows-Wheeler transform where you're seeing it. And so what you see is that actually if you have like a lot of runs, they all get grouped together when you do the Burrows-Wheeler transform, which, you know, simplifies the representation. So now let's do the inverse, because we have this stuff, so we'll just do that. So we have our same string from before. We'll first convert it into an NDARRAY. Now we're going to sort the columns, and you have to do this iteratively in a for loop, right, using this naive algorithm. So we just keep calling sort on like the last chunk of the column using .low. And we just walk through it, and then our original string is right here at the top. So we just take the top row from the array, and we're done, right? That's it, the inverse Burrows-Wheeler transform implemented through NDARRAYs. So, yep, that's the idea right there. Okay, conclusion and final thoughts. Well, there's a lot more stuff left to do with this. The big thing is, of course, linear algebra support, which is going to be a large project. And if I can get someone to like do that for me or pay for me to do that or something, that would be awesome. But otherwise, I'm just going to continue working in sort of a you know, limited time capacity. But this is like the big next step, is to figure out how to get like robust and fast linear solvers working on top of NDARRAY. Also, I need to improve sparse array support. The basic stuff now works, but it's not really fast yet. But it can be a lot faster, and I know how to make it faster, but it's just a matter of like taking the time to do it all. Also, tensor operations, I have some ideas about how to do this, but this could be really cool for doing like generalized matrix multiplication. There are a lot of interesting things to say about this, but I actually view this as kind of like a harder thing than linear algebra. So probably linear algebra is the easy, low-hanging fruit. And then finally, also like just better debugging tools, and also like making more people aware of what's going on to like recruit more help into this project and hopefully grow it and make it into something really awesome. So lots of stuff to do, but what's already there is actually pretty useful and can do a lot of cool stuff. And if you want more information, here are some blog posts about how CWise works and some basics of NDARRAYs. There's also modules.gl, which goes into how a lot of the WebGL interoperability is set up right now. And then there's also a lot of people who have helped with this. So there's Max Ogden, who probably introduced me to Node and NPM, and US Kennedy, who's done a lot of work, and Chris Dickinson, Substack, and Kyle, and also Plotley, who's helped pay for some of the visualization stuff that's gotten done. And that's about it. So yeah, with that, I guess I'll just take some questions and then open up the podium. So that's it. Thank you.
That was a little off my hand.
But
I got the idea.
Okay.
So when we talked yesterday about what you were doing, I kind of had hoped that like one person would ask a question, and he did. That makes me very so Ryan, who gave the talk on Turner earlier, he's asked a question. It is very specific to the CWise function operation, and the function that you give to it. Do you do a toString on that and then generate and evaluate the code around it, or how does that work internally?
Yeah, so there's a couple of things going on there. So the way it works right now is that first it loads, well, there's actually 2 ways you can use it. You can either use it directly as CWise, and this will work in both Node.js and in a browser. And what it does is it takes the function as an argument, it calls .toString, it parses the function apart, and then basically recompiles like the optimized routine for it. And it actually does this lazily, So what'll happen is if you call it with like different layouts of NDARRAYs or different formats, it'll dynamically regenerate an optimized loop specifically for those input types. So it basically, and then it'll cache that generated code and reuse it if the function ever gets called in the future, so that it can, basically reuse like the work done by the JIT. But it's basically like just-in-time code generation to create the best possible loop for that. But if you don't want to bring around the Esprima parser dependencies, the actual code generation is very small. So in a browser, if you don't want to require all of Esprima, you can actually use CWise as a transform in Browserify, and then it will only load the code generation, which is like really tiny, like less than a kilobyte. And then that will like reduce your bundle size drastically because Esprima is very large. So yeah, it basically does code generation, but it's not a big deal. It's pretty much what it is.
All right, so a softball. What's the naming of the high and the low function? Where does that come from? Because it doesn't seem intuitive to what they are doing. To like, if you just name them, but I assume they have some. Like,
yeah,
some
they're like upper and lower bounds, right? Like basically, the high function changes the upper bound of the array, and then the low function changes the lower bound.
Okay.
So that's pretty much what it is. Like the problem is like if you want to specify like intervals, there's just like a huge number of different ways to do this, and basically factoring it into the two separate methods reduces sort of the combinatorial explosion of different ways you could write a bound. So instead of having like one method that can take like a huge number of different parameters, you just have two separate methods, and then it's easy.
Right, and it's cheap because all the operations are.
Yeah. Those are all free. Like they're basically nothing to do that.
All right. I think that was kind of covered, but the actual data store are typed arrays, right?
They can be a typed array. In Node, they can also be a buffer. You can also use a regular array, or you can use a custom data type. So you can use whatever you want, and it actually, again, does dynamic code generation for the correct thing. So if you pass it in like your own custom data type, it will actually generate like an optimized getter and setter. So there's not a big difference in performance for any of these things if you choose to use one or the other. So it just works whichever one you pass into it, and it should be fine. The main advantage, though, for using like a custom one is that you can use that to implement a compressed sparse row and compressed sparse column store. And I think I briefly touched on this, but so in like linear algebra, the two like really important formats for storing a sparse matrix are compressed sparse row and compressed sparse column. And the basic way these things work is they either, for each row, you basically only store the non-zero entries, and then you just squish everything else out. Or in a compressed sparse column store, you just do the same thing, but only running along the columns. And if you think about this and what it's actually doing, like for a little bit, you realize that this is kind of pretty much doing the exact same thing as just run length encoding the matrix, but just doing it over two different layouts. So you can actually just think of the actual data for the matrix as being a 1D array that's just compressed via run length encoding. And then you're just doing like lookups into this compressed store. So like an array access becomes a log n operation instead of like a constant time thing to do that. But the big advantage to this, and this is not yet fully exploited in CWise, is that from a compressed array like that's run length encoded, you can speed up traversals, by basically skipping over runs of constant values. And I have plans to implement that, but it's not done yet.
All right, excellent. Have you done any work on persisting ND arrays?
Yeah, there's a couple of different ways to do that, but because it's just a typed array with the other stuff, you can persist a typed array however you like, and that's it. So you could make a module to do that in whatever store you want.
Well, so my background is in databases, so the interesting bit is I have a persistent representation of the ND array, but then parts of it get updated, and then I want to persist the diff, basically, which is not trivial. That's why databases exist, basically.
Oh, yeah.
So
for that, you could implement a custom data store for your ND array, and people have actually done this. So for example, in like Voxel.js, you can actually create like arrays of blocks, and then you can actually view like the sparse chunked data store as an ND array too. And so that you can actually basically if you can persist a 1D array, you can persist an ND array using this module. There's nothing else to do in that. That's the short answer.
Cool. Excellent. That's very good. And where can we find more about the community that develops all this?
Well, I hang out in IRC. That's about it. There's also you can open up an issue on the page, or you can just send me an email. There's
So there's a specific IRC channel for this? Or is it just
not yet. Maybe I should make one, though. I mean, I hang out in usually Substack's secret IRC channel.
Right.
So that's the one.
All right. That's all the questions and all the time that we have for them.
Yep,
Excellent.
okay, bye.
Good job.